Unit 8C, VPN and Wireless, part of the telecommunications section of this class. What's a VPN? A VPN, or Virtual Private Network, enables secure private connections through untrusted network, typically the internet. It involves setting up a virtual private link across the internet. The notion of a VPN is you have this public network called the internet, and you want to emulate the characteristics of a dedicated link within that network. You want to set up something that's private, that's predictable. Some of the uses of a VPN are remote access. Folks who are working away from the office and need a secure way to access the entire network of the office facility. Note that this is different than just picking up email or accessing a few websites where you have to log in with a user ID and password. This means you are actually on your home office network. People who work at home, field workers, so-called road warriors who are constantly traveling, those sort of folks benefit from a remote access VPN. The other main type of VPN is branch office access to central resources, where you have an office at a fixed location, a small office where it doesn't make sense to actually set up a dedicated telecommunication link between the home office and that branch office. Instead, what you do is you set up a business DSL or cable link to the internet at that branch site, and then set up a VPN so they can communicate through the VPN to corporate headquarters. Now, VPNs can be either layer 2 at the data link layer, more or less, or layer 3 VPNs. What a layer 2 VPN does is it wraps all of the layers of the communication protocol in a new layer 2. So it takes an entire stack from application down below and then shoves it into an envelope that's a new layer 2. You know, it's kind of like those Russian dolls where there's a doll inside of a doll. It creates a tunnel that hides the old traffic from the application layer down in a new layer 2, and then it wraps it in a layer 3 above that in an IP layer and sends it across the internet. Examples of layer 2 VPNs include point-to-point tunneling protocol, PPTP, which was developed and promulgated by Microsoft, or layer 2 tunneling protocol, L2TP, which was developed by Cisco. Now, a layer 2 VPN is quite different. It actually replaces the network layer IP with a completely different layer 3 protocol called IPSec. IPSec, by the way, is included in IPv6. You're not using IP anymore. You're using a protocol that's different from IP. It resembles it somewhat, but it has its own rules, and those rules include means for encrypting and authenticating the traffic. Most routers out there, all routers on the internet, will handle IPsec very well, and most normal routers, even inside an enterprise, handle it as well too. IPsec is actually the more significant method of creating a secure VPN. There have been some issues with both PPTP and layer 2 tunneling protocol. They have some functional benefits, but for the purposes of security, we typically see them wrapped in something else that's more secure. Now, IPsec works both with IP version 4 and with IP version 6. IP version 4 being the current numbering system, that 32-bit dotted decimal thing you're familiar with, and IP version 6 being 128 bits that tends to be shortened via a convention using colons in the number. The components of IPsec include an authentication header, which guarantees the authenticity of the packets, making sure that somebody in transit can't modify the packets illicitly. The encapsulating security protocol, which provides a confidentiality guarantee for packets by encrypting them. Payload compression, which provides a way to compress the packet before encryption. Of course, you can use this alone if you wish to. And then a method of exchanging keys between partners so that you can enable all of the cryptography required for AH and ESP. So these are the components: Internet Key Exchange, IKE, key negotiation, authentication header, which can be used by itself if you're in a situation where you need to authenticate packets but can't or don't want to use encryption to provide confidentiality, and an ESP, which provides confidentiality and also inherently includes authentication. Now, there's two modes to IPsec: transport and tunnel. Transport mode is client to client, end to end. I'm on a desktop machine in my enterprise, and I have a transport mode IPsec connection to a server across the internet. Everything between my client and that server is encrypted with IPsec. Contrast that with a somewhat different method, which is tunnel or gateway to gateway. This is kind of like the branch office access type of VPN, where it's enterprise to enterprise. A tunnel mode IPsec basically works from some sort of external gateway at my enterprise to the corresponding endpoint gateway at the destination. So my client machine talks normal IP all the way up to the gateway. The gateway in turn translates this into IPsec and sends it out to the gateway on the other side. So you're tunneling across the internet, but not internally within your organization. So these are the components of IPsec and the main modes, transport and tunnel. We also have what's called policy management. Which packets must be secured and how. You specify the IP address for the host and subnet and the socket from which the packet originates. Policy management is typically one way, so for a full end-to-end communication, you have to specify a policy for from here to there, and in a second policy from there to here, back again. It's actually not too difficult to set this up in Windows using the management console. There's some articles under the web links for this class that show you how to do this. If you're using Windows, you may want to play around with this a bit and just familiarize yourself. It's all pretty much point and click, actually. Now, another type of VPN actually works at the session layer, the so-called SSL VPNs. They use SSL or TLS at the session layer to encapsulate or package traffic. Since SSL is already embedded in web browsers, you can leverage this ubiquitous presence of SSL in every common web browser to simplify implementation. Typically, this involves a Java client to create the traffic tunnel. What you're doing is you're not just having a browser talk to a browser, but you're using the browser to receive the SSL traffic and then funneling it through a Java applet or application in order to create a virtual network connection on your own machine. The types of this involve are the SSL portal VPN, which is a web page SSL enabled that's a portal to other web services. You know, I think it's mentioned in a textbook, but personally I think this is just marginally falls under the classification of a VPN. And in an SSL tunnel VPN, a web page that provides a tunnel for sending network traffic to non-web services like file shares, file transfers, and so forth. The tunnel VPN is a true VPN in a sense that you have an IP address on the destination network, and you can access and route traffic through that destination network just as though you were there. VPN authentication. We've mentioned key exchange, but authentication is required to authenticate the end users to the VPN. There are several types of authentication here. They're used for not just VPNs, but have historically been used for things like dial-up access and other types of access as well. There's password authentication protocol, PAP, which is a very old sort of authentication protocol, which is entirely clear text. It dates back to the days when you would authenticate via modem to an internet service provider, and you sort of hoped and trusted that that dial-up line between your home and the service provider's point of presence was protected. I mean, it went through the phone company, and of course those guys aren't going to eavesdrop or intercept your traffic, right? The other one is called Challenge Handshake Authentication Protocol, or CHAP, which involves a bit of cryptography, not highly sophisticated, but it doesn't send the password in the clear. Deal is, these two are bad. They're broken. Even CHAP is broken. You know, there are many attacks that have been around for quite a while. Any protocol that uses PAP or CHAP is inherently not secure. So what we have instead is this framework, the Extensible Authentication Protocol, or EAP. It provides a process, a framework, you know, a set of rules for implementing authentication protocols. And then you can use this framework to create specific protocols, you know, by specifying, you know, types of authentication, types of cryptography, types of hashing, etc. There are instances of EAP that have been implemented for things such as wireless LAN, mobile wireless, and for VPNs as well. So EAP is just kind of a general scheme or design for doing secure authentication, but you have to take that general design and implement it in a specific way. So you have methods of EAP. Now on to wireless. The main sort of wireless communication we have that you're probably familiar with is 802.11. It's the wireless LAN standard. It connects you into a wired network. It is in effect a data link protocol that can encapsulate or package IP or other routing protocols through the airwaves to an access point through a router out to the internet. So it's just like Ethernet. It's a full-on LAN protocol. It's the most common one here. There are several different variants of 802.11, as specified by the different data link and even the physical layer protocols. Among other things, they use different frequency spectrums, different ways of modulating the frequency, etc. You also have, as wireless, something called Bluetooth, which is intended for short-range inter-device connectivity, connecting headphones to a computer, connecting a wireless keyboard to a computer, connecting your mobile phone to a computer or some other device. Like I connect my mobile phone to my squawk box in my car so I can have those early morning conference calls on the way into work. That uses Bluetooth. Bluetooth is a type of wireless communication, and it has its own layer 2 and layer 1 protocol stack as well. And it is possible to send networking traffic through Bluetooth if you've got the right drivers and the right software. It's not typically used for that, but it's possible. Another one you can be aware of, because we've got stuff like the Internet of Things, or at the very least your power company doesn't want to pay readers to go out and go on your property, read your meter, and perhaps get bitten by your dog. They would rather do it remotely, not have to hire all these people, and not have to deal with that. So there's a protocol that's been around for a few years, and you'll probably see more about it, called Zigbee. It's very low power, very low data rate. It's designed for long battery life. It's designed for devices where you just sort of install them, let them sit, let them communicate wireless to other devices, and then you never have to touch them again. It's typically used for monitoring and control devices that don't have access to power supplies. Like if you want to put a Zigbee device on a gas meter, a water meter, etc. The electric meter, obviously there's some electricity there, but you might want to use a Zigbee device because you may not want to tap the home electricity to power it. So it's intended for that purpose as well. So these are the major wireless communication protocols out there in the field. Now the layer 1 of the communication protocols, when we talk about wireless, involves what frequency bands, what specific frequency channels, what type of modulation, how amplitude, frequency, and phase changes convey information in different manners. And here are some of the examples. Frequency hopping spread spectrum is used by some old legacy 802.11 as well as Bluetooth. And it basically sends a signal jumping around a frequency band at a very rapid rate. It does this in order to make more efficient use of the frequency itself, as well as to avoid noise. Another form of modulation that involves spreading a signal across a band, again to avoid noise and make more efficient use, is called direct sequence, in which case you mix a signal containing a pseudo-random variant of a frequency in with a modulation, and it kind of spreads it out a bit. It doesn't hop, but it flattens it over the entire band in a predictable fashion. And then the last one we have is something called orthogonal frequency division multiplexing. Don't worry about that. If you need to know more, you can look it up. Now, layer 2 of wireless involves the framing, how the bits are set up. We've just talked about layer 1, which is modulation, frequency, stuff like that. Different frame types are used to establish and maintain connectivity. And we're going to talk here specifically about 802.11. There's 3 types of frames. There's a management frame, which deals with management of the network itself, things like beacons, probes, and authentication to the network. So that's one category of frame we have, and this is all layer 2, by the way. It's completely separate from layer 3, layer 4, and application management and authentication. Then you have the data frames, which is the payload, which is the actual data itself. Something to bear in mind with 802.11 wireless is even the most advanced wireless encryption at the data link level. The payload is actually the only thing encrypted. All of the management stuff is basically unencrypted, as well as the header information for the data frames themselves. And then lastly, you have control frames. They manage the data layer 2 session itself, acknowledging receipt of frames, handling things like flow control, making sure the sender and receiver can manage the flow of data at a consistent rate, speeding up and slowing that down. You know, if a frame isn't received properly, telling the sender to please resend it, etc. That's what a control frame is about. So you've got these 3 distinct type of frames for 802.11. Now, security problems with wireless. First off, assume that eavesdropping happens. You know, lowering the power using directional antennas doesn't do a thing because the attackers always have better antennas than you. An attacker can always get an illegal transmitter that will overpower you. Eavesdropping can be assumed. You also, as I mentioned with the powerful transmitters, illicit transmissions can't be stopped. So you have to assume that someone else can hear you, and you have to assume that someone else can send a transmission based on what they heard that will enter your network. This is very different from the wired world where, you know, somebody would actually have to physically enter your premises and go into a wiring closet to do this sort of stuff. Somebody can be parked across the street or, you know, even a mile or so away and pull this sort of stuff on you. You just have to assume it happens. The last thing is denial of service. There is no way to protect against this. Your availability component of CIA cannot be provided in wireless communication. There is an attack that's one of the guys in the SANS wireless class talks about called the fork in the microwave. Please don't try this, but basically microwave ovens operate in the same frequency range as most 802.11 transmissions. All you have to do is pry open a microwave door and, you know, jam a fork into the interlock, hit the on button, and run like hell because you don't want to get cooked. And you've just demolished every 802.11 connection throughout the entire floor and probably multiple floors of your office. You really cannot prevent somebody from shutting off or jamming your radio frequency. Now, some security controls that exist for 802.11 that we would recommend here, and this goes a bit beyond the book. Use the best possible layer 2 encryption. Don't even think about using WEP. Use some encryption at least. Use WPA2 Enterprise for business, always. This involves linking your access point to a radius server for purposes of authentication. And yes, this is kind of a pain because you have to define your users in a way that they can authenticate using radius. But it's really got some tremendous advantages there by doing this. You've got very strong key encryption and so forth. If you've got a home or small office use, you know, if it's a small business where a radius server isn't an option, or home use, use WPA2 pre-shared key and make sure the pre-shared key is very, very strong because there are dictionary attacks against these. Folks will just try to log into an access point trying every possible pre-shared key there is using literally phrases in a dictionary. The only way to avoid that sort of attack is using a very long, very complex passphrase. Use upper layer encryption as well. Use VPNs if it's something very sensitive. You know, if it's a enterprise environment and you're very concerned about confidentiality and integrity, or always make sure that if you're accessing websites over wireless that it's done using HTTPS, not just plain old HTTP, and that you pay attention to the certs, and if there's an invalid cert you don't go to the site. Treat your wireless network as untrusted in general and place it in a DMZ, in one of those DMZ zones that we talked about in a prior class about firewalls. You shouldn't put wireless networks on your internal network where all of your servers and your end users are. You should put it sort of outside in a subnet. Watch for rogue access points and clients. Wireless intrusion detection systems are something that can be very useful here. Make sure that access points that don't belong don't suddenly show up in your enterprise connected to your wired network. And watch out for folks who aren't supposed to be connecting to your networks attempting to do so. You know, make sure you know what your valid MAC addresses for your wireless clients are in an enterprise environment. And if you see a MAC address that doesn't belong, figure out where it's coming from. Denial of service is inherent. Build in redundancy to reduce the impact. You can't stop somebody from jamming your network deliberately or inadvertently, and believe me, inadvertently can happen quite a bit. Make sure that you don't depend on wireless for critical functions, that there's some redundancy in your operations. That means that if the wireless is down, people can fall back on wired or some other method of accessing the network. In general, Most of the suggestions the book makes on page 728 to 729 under War Driving for Wireless LANs are completely useless. Don't follow these in the real world. It's a chance they might ask you about these in a CISSP exam, in which case you may want to follow the book. But I'm going to refer you to an old article here called The 6 Dumbest Ways to Secure a Wireless LAN. It came out in 2007, and it's just as valid then as it is now. If hiding your SSID, meaning not broadcasting it, restricting access to MAC addresses, and lowering your power level were completely useless in 2007, they certainly are completely useless. Follow the advice I gave you in a prior slide. Use the best possible encryption, use upper layer encryption, place your wireless access point in a DMZ, watch for rogues, and do what you can legally and ethically to knock them off your LAN, and just assume the fact that somebody is eavesdropping and somebody can bring down your wireless LAN, okay? That's it. Thank you.